Hello and welcome to the fourth and final flip learning session that we're going to be putting together for this unit of work, looking at properties of materials, and that's really what we're going to be focusing on today. We've done the stuff on stress and strain and Hooke's law and Young's modulus. Now I actually want to focus on what does this mean for the materials themselves. So first things first, I've got up here some keywords. 8 keywords and 8 key terms that you need to be able to use correctly in a scientific, physical manner, rather than just the sort of everyday usage that we see. So what I'd like you to do is pause the video, and on your worksheet, can you write a definition for each one of these key terms that we've got? Use again the book, use again your textbooks, any other books that you might have, and the internet is a good place to start, but make sure that we're talking about the physics, the science definition, the engineering definition for these words, not necessarily the general English usage. Pause the video and have a go at that for me now. Okay, so these key words then. Let's start off with our first one. Let's have a think about brittle. Now, brittle materials break suddenly and catastrophically with rough edges. Once started, cracks propagate, and they propagate very easily. So bricks are a good example of a brittle material. Another really good example of a brittle material is a biscuit. So if you snap a biscuit, it just all of a sudden it just goes and the whole biscuit snaps in half, and you get those really rough edges to it. Well, that would suggest that biscuits are brittle materials. Go down to the kitchen now, go and try one out, see if you can find a biscuit and just snap it in half, and you'll see exactly what a brittle material is. So hopefully you've got something like that as your definition. So tough then. Tough materials. This is the opposite of brittle. Okay, the material resists cracks, propagation, and so distorts rather than breaking. Nylon is a really good example of a tough material. Okay, so we often see nylon in clothes, also used in many other applications as well, but nylon being a really good example of a tough material. Strong materials. Okay, so these strong materials are materials that need a large stress. Okay, don't forget we know the proper definition for stress as well. So we need a large stress to distort it, so things like steel, titanium alloys, rubber, glass, wood. Now wood's really interesting because it depends on the way in which the grain runs, but wood can be really strong, and cotton, interestingly again, cotton is a really strong material. Hard materials, so hard materials are not easily cut, okay, so things like diamond, okay, diamond being the hardest material known to man, and that's an example of a really hard material. Hard materials are measured on the Mohs hardness scale, okay, and the opposite of hard is soft. Okay, so for example, graphite is an example of a soft material. Now, diamond and graphite are really interesting cases because actually they're the same things. They're carbon, it's just pure carbon, but because they're bonded together in such a way, it gives the material very different properties. And that tells us quite a bit actually, because that tells us that actually it's the way the particles within the material are structured that gives the material these kind of properties that we're talking about and that we're interested in. So that's something to bear in mind and have a think about, because we will talk about that a little bit more in the lesson. Stiff materials, so stiff materials are rigid, they're not easy to bend. Okay, hopefully that's pretty straightforward. And malleable, now malleable and ductile were the last two. Now these are really ones that we have to be really careful about, because there's subtle difference between the two. So malleable materials change shape but does not crack when subject to sudden large forces. Many metals are malleable. Okay, so the key one here is that it's a sudden force. Okay, so it doesn't crack when a sudden force is applied, which compared to a ductile material, okay, which is a material that changes shape rather than cracking, again, just like malleable, but when subjected to a large but steady applied force. And again, we can use ductile to describe many metals, including things like copper. Okay, now final little bit for this session. Like a straw, we're going to look at 3 different strain and stress graphs, stress-strain graphs. Okay, what I'd like you to do for me is, can you plot a stress-strain curve for a ductile material. Have a think. What do you think a ductile material, how is a ductile material going to respond? But bearing in mind we've looked at ductile materials in class, so have a go and see if you can draw a stress strain graph for us. Pause the video and have a go on your sheet. Okay, hopefully you've had a go at that, and hopefully you might have drawn something that looks a little bit like that. Now, different materials have slightly different graphs, but it should be something like this. Okay, and let's see if we can add on some key labels here. So we have this point here, okay, which I'll call P, okay, is the limit of proportionality. Sorry, it's a bit of a mouthful. So I'm going to add that onto my graph. Okay, I suggest you do the same. Okay, limit of proportionality. And all this is this is the place where the linear part of the graph stops. Now it's not quite the same as the elastic limit, okay, which is up here. Okay, and that's because at the elastic limit, okay, the material will still return to its original shape, okay, but it's not happening in a linear fashion. That change isn't happening linearly anymore, okay, it's happening in a non-linear fashion. And then finally, the final key area that I want to point out is this point here, which is the UTS, or the ultimate tensile strength of the material. Okay, so those three labels, make sure you've added them onto your graph: the limit of proportionality, the elastic limit, and the ultimate tensile strength, which I've just drawn onto the graph on the board here. Okay, and make sure your graph is of a similar shape to that as well. Pause the video and make sure you've updated your graph, and then once you've done that, we'll carry on. Okay, if you've all done there, then let's move on. I'd like to do the same again, but can we now draw a graph for a brittle material? How is a brittle material going to look on a stress strain graph? Pause the video, have a go for a brittle material now. Okay, brittle material, so let's have a go. Okay, nice and easy graph actually. Hopefully what you've drawn is a nice straight line. Okay, something that looks like that, which, if we could go back to our definition of a brittle material. Okay, there we go. Okay, a brittle material is one that breaks suddenly and catastrophically with rough edges. Once started, cracks propagate easily. Okay, so that's suggesting to us that it's going to happen very suddenly. So there's going to be no area of plastic deformation. There's going to be no inclination that it's about to break. Okay, and it's going to break completely. Okay, so once it starts to go, once it starts to deform, okay, it will break completely. It will be a catastrophic break. So that leaves us with a graph that looks pretty much like this, okay? All of a sudden we've got a very, very sudden breaking where there is no stress or strain able to be applied to the material, okay? It will be a linear line, okay? It will be a straight line. But yeah, quite a nice simple graph there. The final graph I'd like you to have a go at is for a polymer, okay? For what might a graph look if we were to draw a polymer on the board? Now, think back to what we did back in, I think it was the first lesson we did, when we looked at elastic bands. Rubber is a polymer. So what might our stress strain graph look like for a polymer? Pause the video and have a quick go. Okay, so for a polymeric material, okay, we're going to draw a graph that looks something that a bit like that. Okay, and that's because that goes back to what we talked about in the lesson with all those long chains of molecules, okay, that make up the polymer. They're all crumpled up and they're all over the place, so it's like a plate of spaghetti to start with. But as we apply that force, as we start to stretch it out, they start to elongate, okay? And that's exactly what's happening in this area here. That's what this graph is describing, okay? This elongation of those molecules, okay? And then at this area here, we get those molecules where they can't stretch any longer. Ooh, let's just move that back. Okay, so this area here, those molecules can't stretch any longer, and all of a sudden we have a sudden break in the material. Okay, so just like an elastic band, okay, you stretch it and the first bit is really easy to stretch, and then all of a sudden it gets really, really hard, and then all of a sudden the elastic band will break. Okay, so hopefully you've got a graph that looks like that. Hopefully you've got 3 graphs now on your sheet, as well as those 8 key definitions. Let's finally move on to our final thing. I've got here a piece of bone, okay? What I'd like you to do is using and thinking about the keywords that we talked about right at the start, those 8 key terms. Which one of those, how many of those, which of those would you use to describe bone? Okay, bone as a material. Okay, is it brittle, is it tough, is it strong? Is it hard? Is it soft, stiff, malleable, or ductile? Have a think, okay? Have a think about that. And that's the final thing I'd like you to do on this flip learning session, okay? But once you have done that on your sheet, I'd like you just to take a moment just to think back, reflect on the whole flip learning experience. This is our final session, so it's important that we consider how effective it's actually been. So, if you could bring with you to your lesson not only the sheet from this final flip, but also from all the other lessons that we've done and all of our other flipped sessions, so we can have a conversation about how effective it's been. Finally, don't forget to respond on Edmodo as to how effective you found it, and of course, if there are any questions, don't forget to ask them in the comments section. Other than that, I will see you in the lesson. Thank you very much.